two topics on our menu for the next discussions is narrowband amplifiers, and then we'll follow it up by wideband amplifiers. What we have discussed so far is the usual bandwidth that can be obtained with RC coupled or other kinds of amplifiers. We shall consider the two extreme cases, very narrowband and then very wideband amplifiers. Today we discuss narrowband amplifiers or tuned amplifiers. A tuned amplifier basically is required to obtain a band pass characteristic with a narrow band. That is, the characteristic that we desire to obtain is of this type. Where we characterize this characteristic by means of several parameters. And one of them is this is the response versus frequency. This is the characteristic that we want from a tuned amplifier or a narrowband amplifier, and to be specific, let's say the maximum is put at 0 dB. You can always normalize this. You can always normalize the gain so that the maximum is at 0 dB. The response is characterized by the resonance frequency omega 0, the 3 dB bandwidth. If this is minus 3, a 3 dB bandwidth, which is usually denoted by B, capital B, and in addition there is a third parameter that is used in practical circuits, which is the minus 30 dB bandwidth. That is when the characteristic falls down by 30 decibels from the maximum. This is denoted by capital S. Okay, these are the three parameters that are used. Now suppose I have two characteristics, one is this black line and the other is the blue line. Look at this. Suppose I have another characteristic like this. Obviously the blue line is a poorer narrowband amplifier. Although the bandwidth, 3 dB bandwidth is the same, the blue line represents a poor quality narrowband characteristic than the black line, and that is why this bandwidth is important, the 30 dB bandwidth. And usually one defines a parameter, one defines the following parameters. One is omega 0, the other is omega 0 divided by B. This is called the selectivity of the response, also sometimes called the Q of the circuit. As you know, Q is defined for a coil, for a condenser, for an element, but Q is also defined for a circuit by the ratio of the omega 0 to bandwidth, and the ratio of S to B. The ratio of S to B is called the skirt selectivity. It is a measure of the slope of fall at the 3 dB points. It is a measure of the slope of fall. Obviously this slope, have I made a mistake? Okay, S by B. Do you want S by B to be high or low? Low. So it should really, it's a misnomer, it should really be called skirt rejectivity. Isn't that right? But anyway, this is the definition, S by B. S by B for the black characteristic is lower than S by B for the blue one, but the black one is preferable. So for skirt selectivity you require a low value, for omega 0 by B this selectivity you require a high value. There is a slight contradiction here. But anyway, what we for a few hundred kilohertz to a few hundred megahertz, such a characteristic is obtained by a tuned circuit, an RLC tuned circuit, and a very simple tuned circuit. We shall consider tuned amplifiers of the following class, class A only. We will not consider any other type. Class A and voltage amplifier. These are the usual demands in practice. One of the examples of a tuned amplifier is in the IF stage or the RF stage of a radio receiver or a TV receiver. You know, the intermediate frequency stage, you require a tuned amplifier like this, or in the RF stage of a radio receiver. And the simple circuit is a simple way that you can achieve such a characteristic to bring variety into experience. Let us use a FET amplifier. What you want is, I am omitting the bias circuits. What you want is, you have a VI and the load of the drain should consist of a parallel RLC circuit. Let us call this RL, CL, and in addition you have to use an inductance L. If I omit the the biasing circuits, well, this is the circuit for a single tuned amplifier. Single tuned because it uses only one tuned circuit. Okay. Now the equivalent circuit of this would be VI plus minus, then GMVI. I will use this as R, I will use this as C, and I will use an L here. Can you tell me why these are different? Why R is not RL? This R combines RL with small r subscript small d, the dynamic resistance of the FET. Quite so. What is C? C combines CL plus CDS between the drain and source and any stray capacitance that might crop up in this circuit. So this is the total circuit, and you know that the gain of this stage is very easy to see. V0 by Vi would be equal to minus Gm times the impedance of this circuit, which is the 1 by the admittance of this circuit, 1 by R plus SC plus 1 over SL. I can write this gain V0 by Vi as equal to minus Gm divided by C. If I take C common, then I get 1 by, if I take C common, then 1 by CR plus S plus 1 over SLC. Okay? Yes.
Could you please show the previous slide?
Previous slide, yes. You don't have a question, or you wanted to write it down. Okay. Now, you recognize that this is a simple second order circuit. It has, does it have a pole? It does. How many? 2. And does it have a 0? At the origin. 1 0 at the origin. So the pole 0 diagram is this. Are these poles complex or real? They could be. They could be real also, but a real pole does not serve much of a purpose. You require them to be complex, not only complex, you require them to be close to the j omega axis. Okay? Close to the j omega axis. The real part of this pole should be as small as possible. Who determines the real part? The resistance R. The resistance R determines the real part. Now, you want R to be high or low in this case? Wrong. You require this R to be as high as possible. If this was infinity, then the pole should have been exactly on the j omega axis. Okay. Now, V0 by Vi, when you put this is equal to j omega, it's minus Gm by C 1 over CR plus J omega minus 1 by omega LC, which makes it clear that the maximum value, maximum magnitude is reached at the frequency omega 0 equal to 1 by square root LC, that is when this is equal, this is 0, and the maximum value is GMR, and the bandwidth B, can you guess what the bandwidth is?
R by L.
1 by RC. It is this factor which is the bandwidth, 1 by CR. You must have done this in your circuit theory class, but if you have not done it, take the magnitude, find out the values at which the magnitude is 1 by root 2, and then find that this is the story. That is, what we have achieved is something like this. Omega 0, this magnitude V0 by Vi magnitude is GMR, and if this is GMR divided by root 2, then this B is equal to 1 by CR, and therefore the Q of this circuit, the selectivity, which is omega 0 divided by bandwidth, is equal to omega 0 CR. It is proportional to R. The higher R is, the higher is the value of Q. Okay. I will not do the algebra because you must have done it in the circuit theory class. Now the problem, where is the problem? The problem is that my circuit, I drew the circuit as R, C and L. So long as I can realize such a tuned circuit is wonderful, but unfortunately I can't do that. What I realize is whenever there is an inductance, there is a resistance. So this inductance is not a pure inductance, it comes in series with a resistance, let us call it RS, which causes the resonance frequency to change, the maximum gain to change, and everything else. Also analysis. In the analysis, you see you have to put j omega L plus RS instead of RS. However, such inductances are always described or characterized by the inductance and its Q parameter. We call it Q0 at the frequency at which you want to use it. Now what is Q0? Omega 0 L divided by RS, the series resistance. This describes the coil. The coil has an inductance and a value of Q. Q is this. Now it would have been wonderful if this series combination could be replaced by a parallel pure inductance LP and a pure resistance RP. Obviously, in general, at an arbitrary frequency, you cannot do that. You cannot do that, okay? But at a particular frequency, at the resonance frequency, this is possible to be done. Why should we do this? Because then it eases the analysis. I will have the same circuit again if I can reduce it to this form, and reduction it to this form is not a very difficult problem. The impedance of the inductor at the frequency omega 0, at the resonance frequency, is j omega L plus j omega naught L plus RS, okay, which I can write as 1 over j omega naught L, then 1 minus RS. This is the admittance. I beg your pardon. This is the admittance y of j omega naught. If I take j omega naught L out, then I get 1 minus j RS divided by omega naught L. Agreed? Which is equal to, look at this derivation, 1 by 1 minus j by q naught. Agreed? I can write this as 1 by j omega naught L, 1 plus 1 over q naught squared, 1 plus j by q naught. All right, and and if Q naught is much greater than 1, Q naught squared much greater than 1, so even for Q naught equal to 3, this should be true. Q naught squared is approximately 10. If Q naught squared is much greater than 1, then the admittance y of j omega naught is equal to 1 over j omega naught L 1 plus j by Q naught, which is equal to approximately 1 by j omega naught L plus, how much is left here, omega naught L Q naught, and therefore LP, this is equivalent to a inductance LP and a resistance RP, where LP is equal to L, the original inductance, and RP is equal to omega 0 L Q naught. You can see now that Q naught is RP by omega naught L. So it is proportional to the resistance, because we have expressed it in the form of a parallel combination. Yes.
So if we want R as large as possible, then why do we need to put an external resistance R at all?
Just a minute. We have to go back to the original circuit. What was your question? If I need R as large as possible, why do I insert this resistance? Okay, any answer? What is this resistance? This is the capital R sub capital D. You require a resistance to bias the FET, and it is that resistance in parallel with the dynamic resistance. The resistance is inevitable. It shall be there. It can be large, but it shall be there. Okay. Now it turns out that in practice, if the frequency, even for moderate frequencies, let us say if the frequency is 1 megahertz, if the frequency is 1 megahertz, then the inductance and capacitance should satisfy the relation LC equal to 4 pi squared, no, LC equal to 1 by 4 pi squared F naught squared. Agree? Right? So in this case it is 1 by 4 pi squared 10 to the 12, the product of L and C. A choice, one typical choice is, let us say L equal to 3.18 microhenry and C is equal to 7958 picofarad. Now this is usually a very small value of inductance, very small value of inductance. If you want a Q of, let us say 100, getting a Q of 100 with a small inductance like this is a difficult problem. Also this capacitance is a large capacitance. If I can reduce it further, it would be to our advantage. The smaller the capacitor, the smaller is the size, and the better is its loss characteristics. Agreed? The higher the capacitor, the bigger is the loss. That is why electrolytic capacitors cannot be used in such circuits at all, because they have a very low resistance in parallel. Okay. So what one does is, if the values that you require are not manageable, then you use a transformer, and the transformer is usually an auto transformer, not the two coils separated by a distance. It is usually the same coil which is tapped, and at radio frequencies this can be very easily made by taking a ferrite core and winding a coil around it. Suppose, and then taking a tap, let us say from here to here. What you make is a large inductance, okay, of the same Q, and then you transform this to a smaller inductance across this. Agreed? The Q is preserved. Not only that, if you make this transformation, then you can use a smaller capacitor across this to transform it into a, I beg your pardon, yes, to transform this into a larger capacitance. Okay. Let us see what these relationships are. Suppose I want to make a tuned circuit like this, R, L and C. I want to make a circuit like this where L is very small and C is very large. I want to use a convenient auto transformer or a tapped coil to make this circuit. I want to use a smaller capacitor and I want to use a larger inductance. This is very common in RF circuits. What one does is the following. One takes an inductance and suppose I terminate in a capacitance C prime and L prime. Suppose the number of turns in this is N2 and then I take a tap. Suppose the number of turns is N1. Then at these terminals the inductance that you will see would be L equal to L prime, yes, multiplied by N1 by N2 squared. Is that clear? The impedance reflected here, the inductive impedance would be j omega L prime multiplied by the turns ratio whole squared. Therefore, the inductance is multiplied by this. Is that clear? Okay. So, L prime that you make is L N2 by N1 whole squared, which is obviously larger than what you required. Similarly, the capacitance that you see here would be C would be equal to C prime divided by N1 by N2 whole squared, which is equal to C prime N2 by N1 whole squared. Therefore, the actual capacitance that you use is less than the capacitance that is required. Okay. Is that clear? For example, if considering the previous example, 1 megahertz is your tuned frequency, resonance frequency, and suppose you use a turns ratio of 3, that is, which is equal to N2 divided by N1. Then one can very easily see that you can do with an inductance instead of 3.18 microhenry, you can do it in inductance which is 9 times larger, that is 28.6 microhenry, and a capacitance C prime which is 9 times smaller. So you can do it 884 PAF. Can you tell me any other reason why this auto transformer facility would be useful? Any other reason? Suppose the capacitance, you see, while inductance you can fine tune by putting an extra turn or half a turn or a quarter turn. Capacitance, there is nothing that you can do. It's only standard values which are available. What you can do is you take a standard value, then use a variable capacitor which is called, oh no, variable capacitor. Varactor is diode. Okay. Variable capacitor is called a trimmer. The barbers use a trimmer. It has a mechanical control. You see, what it is a small parallel plate capacitor. Okay, small a button and another button. Put a dielectric in between. A metal button and a metal button. Put a dielectric in between. Okay. Area is variable. Okay. So there is a screw at the top which you can drive and vary the capacitance. But it's messy. One would be perfectly comfortable. If it's a fixed frequency, 1 megahertz, I don't want all this mess. I want a fixed capacitance, and therefore an auto transformer there helps. You can slightly change the tap to make this a standard value which is available in the laboratory. Okay. For example, 792 PAF, if I remember, that's a standard value. Okay, some standard value that is available in the lab. So, an auto transformer is used. An auto transformer is also used if you require to couple a tuned amplifier to a next stage. Let's say you have a tuned amplifier whose equivalent circuit is, let's say, like this: some current, then a resistance R1 and a resistance C1 and an inductance L. Suppose you want to couple this to the next stage, which is a common emitter amplifier. Okay, common emitter amplifier. Obviously, what this will see, if you connect it directly, then what this will see is a parallel combination of R pi and C pi. Perhaps there would be a CM also. Alright. Now, what is this R pi going to do? It is going to reduce the parallel resistance. What effect does that have on the characteristic? The bandwidth broadens, the bandwidth increases. It is a parallel resistance, and therefore it changes the characteristic of this tuned circuit. What you would like is a transformer from here to here such that the loading effect on the tuned circuit is as little as possible. So what you do is, instead of coupling directly, you couple like this. There is a problem. Okay. You couple like this. You use an I, R1, C1, then this inductance you make it into a tapped coil. That is, don't couple the total inductance, but take a tap here and then couple to the next stage. The equivalent circuit, suppose the turns ratio is n:1. Suppose the turns ratio is n:1. Then the equivalent circuit, next stage, which is R pi, let's say parallel C pi. Then the equivalent circuit would be I R1 C1 L, and in parallel will come what? It will come a resistance which is R pi times n squared. Isn't that right? So you reflect a higher resistance to the tuned circuit, and the capacitance would be, what about the capacitance? It will be C pi divided by n squared, therefore a smaller capacitance. In other words, the detuning of this circuit would be minimized. You can choose your n. If n is 3.3, then it's 10 times less. If C pi is 10 puff, it would reflect only 1 puff here. So the effect on C1 would be minimal. Effect on detuning would be minimal. So an auto transformer is also used in that connection. Any question? Okay. Now suppose you have made a tuned amplifier whose selectivity or the skirt selectivity is not of the proper value. You want to sharpen it. You have a characteristic like this. You want to sharpen it. Let's normalize the maximum to 1. How can you sharpen it? How can you make it into, how can you convert this into a circuit like this? If you cascade 2 such stages, if you connect 2 such stages in cascade, then the resonance frequency remains the same. It becomes this characteristic will be the square of the other characteristic, which means that wherever there was 0.9 would now become 0.81, and therefore the selectivity increases. All right.
Increase R1 to decrease the value.
Could I?
Increase R1.
There are limitations. R1 cannot be increased beyond, let's say, small r subscript small d. There are limitations. With that, you do not satisfy the prescribed characteristics, so therefore you cascade 2 such stages. Or you could also do this, that use 2 tuned circuits tuned at the same frequency, one at the input of the amplifier and the other at the output of the amplifier. You can do that. Let us see what this circuit looks like. Is the point clear? You may not use two amplifiers, you may use the same active device, but a tuned circuit at the input and a tuned circuit at the output. Let us see what this circuit looks like and what is its problem. I am going to draw now a typical RF amplifier circuit and then I shall discuss what the problems are. This is infinitely large. You want to use a tuned circuit as the load, so you have L2, C2 and the losses R2 plus VCC. This R2 may not be externally added, it might be simply the losses of L2. You know that L2 will be a series combination of L2 and RS2, which can be converted into L2 parallel R2. And then this is your output, some coupling capacitor which is infinitely large, V0. At the input, let us look at it as a current amplifier, that is the GMVI perhaps of the previous stage. At the input we use a parallel circuit C1 L1. I do not use a resistance, that resistance will inevitably come from the from this circuit. So a coupling capacitor which is infinitely large. Then I have the biasing arrangement, some resistance RB1, and if you want it to be AC open, then you use an RF choke here, you use an RF choke here also, so that RB1 parallel R2 does not load L1, and then you have RB2 to ground. The problem in such cases, in such amplifiers, is this inevitable small capacitor which causes havoc, C mu. R pi, C pi can be taken care of, R pi will contribute to the damping of this tuned circuit. C pi can be combined with C1, but what about C mu? One may argue that C mu can be reflected as a Miller capacitance at the input. How would you reflect? Because this load is no longer a purely resistive load, and therefore what will be reflected is not a pure resistance, but it would be resistance and reactance, alright, and therefore this will totally detune the input tuned circuit. Agreed? Worse still, you see, if you have this characteristic, the output characteristic like this, and another characteristic, let us say like this, if the two resonance frequencies do not agree with each other, then you are actually widening the bandwidth. Isn't that right? And therefore C mu plays havoc.
Sir?
Yes.
But at the resonance frequency, the tuned circuit will have a
at the resonance frequency. Now it is not an oscillator circuit. We have to accept a band of frequencies, and therefore you can no longer consider this as a pure resistance. Okay, you have to consider around this frequency where L2, C2 both come into effect. I was expecting this question. While in an oscillator circuit, a single frequency oscillator, we could do that. We could take the resonance value, but not in a narrow band, not in a tuned amplifier, where there is a band of frequencies involved, so the reactances have also to be considered. Worst problem is that you see that this is nothing different from a Hartley oscillator. Isn't it right? A Hartley oscillator has a capacitance and two inductances. At a frequency, when this behaves as an inductance and this behaves as an inductance, it might oscillate. And this is usually what happens. Whenever you want to make a tuned amplifier, it usually oscillates. It's a fact of nature, and therefore the joke is, if you want to make an amplifier, make an oscillator. It will not oscillate, it will amplify. If you want to make an amplifier, if you want to make a oscillator, make an amplifier. Okay, that's the joke. But this is a real problem, and there is a lot of effort, which is RF design is much more difficult than audio design or low frequency design. Okay. So what one does is one tries to cancel the effect of C mu, and this process is what is known as neutralization. It is a standard practice in RF amplifiers. You have to do something, you have to make some efforts to neutralize the effect of C mu. Okay. And the neutralization, can you suggest a very simple method of neutralizing this? Short it, then the collector will be shorted to base, no amplification. No amplification. Yes, very simple minded procedure. At a negative capacitance, where do I get that? The storekeeper will call you crazy if you ask for a negative capacitance.
I don't negative capacitance as such. I think it's circuit that will reflect some
What is that circuit? Okay. One of the simple minded procedures is add an inductance in parallel. But you cannot add an inductance in parallel because the DC will go where? So, complication. You have to use a blocking capacitor here. You see, C mu, if you want to neutralize its effect, you have to have a CB which is very large, then an inductor, a small inductor, and at 100 megahertz, a piece of wire would do. A piece of wire, a straight piece of wire has an inductance. That would do. So making this inductance is not a problem. But what is the problem is that this inductance should be such that the impedance of this is approximately infinity, not only at omega 0 but around this. In other words, this is a very critical adjustment. Nevertheless, it is done. How it is done is the following. Since an inductance tuning, a small inductance, tuning a small inductance is a very difficult problem. You have to use a core, and the core has to be adjustable and things like that. So what one does is take the available nearest value of inductance, connect it. Then obviously C mu, well, we cannot adjust it, C mu is internal, but we can always increase its value by using a trimmer, CT, and adjusting a trimmer. A trimmer adjustment is much easier than adjustment of an inductance. Okay, so this is a simple minded procedure, but people soon discovered that it has its own limitations. With age, things change, transistor parameters change, and the circuit which worked wonderfully on the 23rd of March, on the 1st of April, it starts oscillating. Okay, so this neutralization has very limited application. What one does is one uses circuits in which neutralization is not required. Can you mention a circuit in which C mu can play no havoc? Miller effect is absent. Can you mention a simple transistor circuit? FET? FET has C, G, D. Which plays havoc again? It plays the role of C mu.
So we change the biasing to common.
No. Pardon me?
The common base.
The common base. That is the answer. That's what is said. Okay, then you are correct. A common base circuit. Let me look at this. If the base is common, which means the base is grounded, then C mu is simply connects from collector to ground. Okay, and it simply comes in parallel with the load. The load has a capacitance anyway, so it cannot affect. Is that clear? So what one does is two possible circuits. One is a CC CB cascade. Okay, two transistors are used. As a common collector stage is cascaded to a common base. Now in a common base, C mu comes in parallel with the load, so there is no Miller effect. Why a CC? What is the Miller effect in a CC? Okay, C mu. What is the load in a common collector? 0, and therefore 1 plus GMRL is 1, and therefore C mu reflects as only C mu. Alright, so a common collector, common base cascade is a very popular method for increasing the selectivity of a tuned amplifier. The other one is a cascode stage. A cascode stage is one. Have we discussed this earlier? No. A cascode stage is one in which one transistor sits upon another. Okay, this is a cascode stage. One transistor sits upon another. What happens to C mu of this? What is the effective load? What is the effective load that this transistor sees? It's not R pi. No. Effective load. This transistor, the collector, sees what load? It's not R pi. R pi divided by beta, because it's the emitter current. So R pi divided by beta, which is equal to 1 by Gm. Okay, and therefore C mu reflects as 1 plus GMRL, which is 1. So C mu reflects as twice C mu. That's all. It cannot reflect as 100 times C mu. So the effect of C mu is contained. It's made as small as possible. What about the other one? What about this one? What is the effect of C mu? This is a common base, and therefore it comes in parallel with the load.
But in this case, the upper transistor also has capacitances which are
Upper transistor also is capacitance. Which one? C pi? Okay.
and C mu.
No, C pi comes as C pi times,
Divided by
yes?
into beta.
Does it come that way? R pi by beta? Oh, it comes as beta C pi. It comes as a large capacitance. Right? Large capacitance has very low impedance. And therefore its effect on C mu will be negligible. Okay, this is called a cascode combination, and next time we will discuss these two circuits qualitatively and then go into broadbanding techniques.
Mechanics is the name of the game. We play with objects, subjecting them to motion under the application of forces. The rules of the game, known as laws of motion, have been derived from extensive studies on the behavior of bodies in nature, from falling apples to the motion of planets in the sky. The laws enable us to analyze the motion of bodies under the application of forces and to estimate the forces for the design of systems to create the desired effects. The action and effect aspects of mechanics applies to deformable bodies, flow of fluids, continuum, and often extended to socio-economic systems. But we will confine ourselves to the mechanics of rigid bodies and point objects, that's particles. It is not the same laws which apply to the entire expanse of size and velocities of bodies. We shall limit ourselves to classical mechanics. Material objects larger than subatomic particles with speed less than, say, 10% the speed of light obey the laws of classical mechanics. Of course, we shall take the state of rest as a special case of motion being zero. Mechanics is at the core of all science and engineering because of its far-reaching applications in high-rise buildings, flyovers and bridges, in the design of electrical machines, in biomechanics and rehabilitation.
Hello. Internet is the name of the game.
What is the internet?
Can I find some courses being offered?
Can I seek admission to a university?
I want to read a newspaper.
Can I see what's on in London?
Stock market quotes in Wall Street.
Can we hear music and watch video on the internet?
Can I make a flight reservation to Timbuktu?
Auntie, can I play some new games?
Is it possible to search a job?
Can we attach a file on the email?
Yes, this and many more things can be found on the internet. You don't have to go anywhere. Just relax and surf the internet at your place. Now let me log you into Professor K.L. Kumar.
Why to me, Sangeeta? Let us log in to the internet right away. Here we are, riding high. Let me begin with my home page. Our teaching assignments, the faculty development program, and the consultancies. Let me show you what's new.
Shaping of metals by the casting process is one of the oldest occupations of mankind. For example, this ancient coin and the bronze statue of the dancing girl of Mohenjo-daro are products of the age-old casting process. Even the historic iron pillar in the Qutub Minar complex depicts the glory of ancient India in the field of metal casting. There are various methods of casting. In this film, we will talk about the process of sand casting only. For casting, we need molds, and for making molds, sand is most commonly used because of its peculiar properties like refractiveness, thermal stability, flowability, permeability, and easy availability. It is very easy to break the sand molds after casting. Let us get to the details of the casting process. The first step is the preparation of sand for mold making. Once the molding sand is prepared, it has to be tested for permeability, hardness, and strength. So, a standard specimen is first made. In this case, it is the green sand specimen, since it has got water in it. Standard weight is dropped from a fixed height 3 times. After the standard specimen is made, it is first tested to determine the permeability of sand. The permeability is determined by noting the time of passage of fixed volume of air through the specimen under standard conditions. This fracture indicates a failure in shear. After successful testing of sand, the mold making begins. A pattern is placed on a flat, hard board. A small quantity of fresh sand or parting sand is sprinkled on the hard board. After the molds are made, they are transported to the pouring bay, ready to receive the molten metal. The metal is melted in a crucible, which is heated in a pit furnace. Using a pyrometer, the temperature of the molten metal is checked. Metal is then poured rapidly, but with a measured rate. The quantity to be poured depends on the size of the castings and the size of the gating system. After some time, the castings are opened. The mold is knocked out and the metal piece is carefully cleaned and cleared of the sand. Castings are usually allowed to cool in the mold till they reach the room temperature. In some cases, we may resort to quenching.
All engineers in their day-to-day profession often come across electromechanical energy converters, normally known as electrical machines. They comprise electric motors and generators. Why only an engineer? Even a farmer, a housewife, a common man come across them in their day-to-day life. Therefore, it is very essential for us to know how many types of machines are there, what are their parts, how are they made, how do they work, and where are they used. So we shall try to answer some of these questions in this series of film on electrical machines. In the first part of the series, today, we will learn about certain basic and general concepts of electrical machines. We begin with a demonstration of a basic principle. Here is a coil and here is a magnet. You notice that when you bring the magnet near the coil, the meter moves one direction, taken away, moves in another direction. In one direction, out other direction. We observe this deflection more pronounced in this sensitive galvanometer. Both stator and rotor are of electromagnetic structures made up of similar materials and parts. They consist of a magnetic part called the core and electric part called the windings. The core, a typical one shown here, is basically made up of iron, but today would consist of a range of ferromagnetic materials, that is, iron allied with suitable elements to improve magnetic properties. Core is either a solid steel structure or a laminated one. A laminated core is made up of stampings which are stacked together to form the body of the core. Here is a set of laminations or stampings. For example, these are the laminations used in a motor. This is a stator lamination and this is a rotor lamination. They are aligned in this fashion to make the core structure of stator and rotor.
From time immemorial, man has been deriving inspiration from nature. The colorful world fascinated him. He wandered, imitated, and sometimes even competed with nature. Perhaps the accidental imprint of his hand initiated him into printing to create a colorful world around him. We have come a long way since that pleasant experience, in that the art of dyeing and printing today has become the science. However, man's adventurism and greed are altering the balance of natural forces today and are spelling disaster. Environmental pollution is one such example and is a cause for concern. Industrial revolution changed the course of textile industry too, chemical processing industry included. The fruits of advances were reaped by one and all. Today, however, there is a growing concern about the attendant pollution dangers involving certain dyes and chemicals. Maybe the time has come to stop, think, and look back and search for answers in nature itself, the very colorful world that fascinated man in the first place. In the context of dyeing and printing, are natural dyes the answer? Natural dyes are eco-friendly and can be considered as safe dyes. As the awareness in this aspect is increasing, the demand for products dyed with natural dyes is also increasing the world over. In the Indian context, it signifies improved export potential and better earnings for our handloom workers and master artisans. This short film gives a brief but comprehensive view of natural dyes, encompassing the raw materials, the chemistry and classification, conventional dyeing procedures and the limitations, and the role modern technology can play for enhancing the cause of natural dyes and products therefrom.